Hi guys, welcome back. Today we're going to review a little of what we've already done earlier in the year about motion of a particle, and we're going to add a little bit more to it. So first, the review. Hit pause and see if you can remember how to do this problem. Write down all of your answers. Okay, if you don't remember how to do it, then find the notes I gave you called Semester 1 Justifications and look up everything to do with motion of a particle, okay? And if you look at all the justifications, every single justification has the word velocity in it. So all of the things you want to look at for all of these is velocity. All right, so remember, particles moving to the right when velocity is positive. That's the justification for that. Which means since this is velocity, velocity is positive everywhere up here. All of that is above 0. So the answer to that one would be from 5 to 10. Okay, when is the particle stopped? That's when velocity is 0. And so that would be in 3 places, the beginning at 5 and at 10. When does the particle change directions? Well, that's when velocity changes signs. So that would be at 5. T equals 5. Okay, speeding up and slowing down. Before I answer that one, let me do an overall review of what's going on in this picture, okay? So, remember, this is particle moving to the right. This is particle moving left, okay? Now, speed. Speed is the absolute value of velocity. So the speed here is 4. The velocity is also 4. But here the velocity is -4 and the speed is 4. So at the beginning of this problem, we're starting at a speed of 0, but the speed right here is 2. So we're going from a speed of 0 to a speed of 2. That means we are speeding up right there. Okay? So this is speeding up because you're going away from 0 to 2. This is a constant speed. This is a speed of 2 to a speed of 0, so this is slowing down. Okay, then we have from here speed of 0 to speed of 4. That's speeding up. This is a constant speed, and this is slowing down. So to summarize, speeding up, think of that as going away from 0. This is speeding up. This is speeding up. Okay? Slowing down, you're going towards 0, towards 0. So when is the particle speeding up? In these 2 places, 0 to 2 and 5 to 6. 0 to 2 and 5 to 6. Okay, so that's all review. Supposedly you already know that. Here are all of the justifications you're supposed to know already. These are all things we've already done this year, and it's on that piece of paper I gave you of justifications. Now, speed is the tricky one. Speed, when I'm looking at a graph, that's what I just did. I use this definition, and I just think of going away from 0 for speeding up, going towards 0 for slowing down. You can write that here, okay? But you're not actually allowed to use that as a formal justification on the AP exam. You can't say going away from 0. You could just try saying absolute value of velocity and maybe hope for the best. But the real formal justification for speeding up and slowing down is supposed to be this. And you definitely need these guys if you don't have a graph. If you don't have the graph, you have to find velocity and acceleration and do sign charts. Okay? But I didn't worry about that today. We're not going to focus on that today. Today's question is going to be looking at that same situation. Here's stuff you should already know. Looking at that same graph, today's question is going to be, what is the total distance traveled by the particle? Okay, that's today's question. Think about that for a minute. If this is meters per second, then what would the units be for distance? Hopefully you can see that would be meters, right? So how do you get from meters per second to meters? Hopefully remember that means you have to integrate. So how do we integrate a graph? We're looking at area. Okay, so we're looking at the area under the graph. So let's find the areas. Actually, this is the same exact graph from yesterday. So if I did the area of this underneath these things, this is an area of 7 and this is an area of 4. Now, what does that mean in the context of this problem? If this is a particle moving along the x-axis, then it went 7 meters to the left and 14 meters to the right. And that's the area under the curves, okay? So given those two numbers, 7 and 14, I want you to think about that again. Total distance traveled. The particle went 7 meters left and 14 meters to the right. What is the total distance traveled? Okay, hopefully you have your answer. Your answer might have been 7 and your answer might have been 21. Well, which one is it? Okay, think about traveling in my car. When I take my car to school and I go 20 miles, then I go back home 20 miles. Did I drive 0 miles that day? No. I drove 40 miles. What I'm trying to get at is distance is always positive. So we're going to say we went 7 miles and also 14 miles. This is meters. So the answer to this question is 21 meters. The total distance is the absolute value of each of these. Okay, remember, distance, it doesn't matter if I go left or right, I still traveled a positive distance. I can't go a negative distance. So when you justify distance, when they say distance, we want to first find the areas, which means we are doing the integral, okay? But then we want to make each of these pieces positive, so we want the absolute value, okay? And make sure the absolute values are behind the integral, not after the integral. In other words, you don't want it to be this. Oops, that's messy. You don't want this, okay? Think about the difference between those two answers. This one would simply first find the integral, which would be positive 7, because it would give this a negative value, and then it would absolute that and give me an answer of 7. That's not what we want. What we want, okay, what we want is to absolute value each piece first. So I want the absolute value of this and the absolute value of this, and then add them up. Okay, that's what this is doing. All right, so put that in your notes. So if it says total distance, it's the absolute value and the integral of velocity. Now, to help make sense of that a little bit more, let me show you this problem. Now, this problem is not necessarily the most realistic, but it does help make the point, which is the same point I just made on the last slide. Okay, this is the velocity of a bee going back and forth from his hive to a flower, okay? And this bee is a little crazy. He's nuts. Because somehow, if this is his velocity, somehow he manages to go from 0 velocity to 100 immediately. He starts off and just immediately is going at 100, and then he crashes, I guess, and stops, and now he stopped again. He stopped right here. And then he's going at 100 again, and then he stopped. So he keeps crashing. I don't know how he manages to go 100 to 0, 100 to 0. Okay, so what's going on in this picture? All right, so remember, if this is velocity, then this would be, all of this is positive. That's going right, typically. But in this case, that would be him going to the flower. If this is velocity and this is negative, that would typically mean going left. But in this case, it would mean going back to the hive. So what's going on here? This bee is traveling 100 feet per minute to the hive, stops, collects the honey, whatever. Then he's still going at a speed of 100 here, but going in reverse, back to the hive, stop, crash, stop. Then he manages to suddenly start flying again without speeding up to get there. 100 back to the flower, get more honey, stop. And then doesn't make it quite all the way back home in reverse. Okay, now the reason for this is so that we can try to make sense of what we're finding when we find distance, okay? So given this unrealistic scenario where the bee doesn't speed up and just manages to fly and crash and fly and crash and fly and crash, I want you to think for a minute the answer to this question. What is the total distance traveled by the bee? Again, if this is 100 feet per minute for 2 minutes, 100 feet per minute for 2 minutes means that he went how far during that travel? Okay, so he went 200 feet to the flower. Then he stops. Then 200 feet back and stop. Then 200 feet back to the flower and stop. And then, only 100 feet. And then I don't know what happens to the guy. Still, answer this question. Based on the last slide that I showed you, what is the total distance traveled by the bee? And remember, distance cannot be negative. You got your answer? Hopefully you said that the total distance traveled is 700 feet, because even when I drive to school and back from school, I'm traveling a positive distance. Okay, now let's compare that to the other question you're going to be asked. A similar question would be, where did the bee end up? At the end of this problem, where is that bee compared to where he started? Formally, that's known as displacement. But in our class, typically, even on the AP exam, they don't usually use the word displacement. They ask the new position. And it's not often a bee, it's often a particle. Stupid particles moving along lines all the time. Okay, but it's the same idea. So where did the bee end up compared to where he started? Okay, well, that's known as displacement. And when we want to know where he ended up, now it matters whether he went forward or backwards or to the hive and back. So now you assign negative values when you're going backwards. So he went forward 200 or to the hive 200. Nope, that's wrong, sorry. To the flower 200. Then he went back to the hive. So now he's at the beginning, he's at 0. Then he goes another 200 forward or to the flower. And then he goes back 100. So where is the bee compared to where he started? You got your answer? Hopefully you can see he's going forward, backward. He's still 100 feet forward or 100 feet towards the hive or 100 feet either direction, honestly. Okay, I think I was on pause, so I may be repeating myself right now. I'm not sure. Regardless of whether it was the hive or the flower and which one was where, I don't care. The moral of the story is you went forward 200, backwards 200, forward 200, back only 100. Net result, you've stopped 100 feet positive. Okay? Now let's apply that concept to the same problem that we had before, but I'm going to change it up and make it a turtle instead of a particle. Okay, read this question. The areas are the same. We can fill in the same areas. Okay, keep in mind, this starts off a little confusing for some. Keep in mind that this graph that we're given is showing the speed and the direction. It's a velocity graph. It doesn't show where the turtle started. So this starting 2 feet to the right of my mailbox, that's the starting position. That doesn't show up anywhere on this graph. They just have to tell you that. Okay, so we start at a positive 2, in other words. Then we go left 7 and right 14. Okay? So now take a moment to answer that question. We started right 2, we went left 7, and then we went right 14. Where did the turtle end up? Okay, so hopefully you can see that. That is basically 2 plus 7. So it ended up 9 feet, if this is feet, 9 feet to the right of my mailbox. 9 feet right of the mailbox. Now, next question. What if I tried to trick you and I said, I gave you this 2 feet thing. It still started 2 feet to the right of the mailbox, What is the total distance traveled? Okay, listen carefully. I still say the turtle started 2 feet from the right of the mailbox. What is the total distance traveled in 10 seconds? That's a trick question. It doesn't matter where you start. When I ask total distance traveled, the turtle went 7 and 14, 21 feet. You ignore the 2. Okay? So let's summarize the difference in these things. If I ask distance traveled, it doesn't matter where you start. It's irrelevant the starting position. For distance traveled, it's the absolute value of the 2 areas. Okay? And add those up. In symbolic form, that means it's the integral of the absolute value of velocity from whatever points, from whatever time frame. Okay? Versus new position. If I ask where did it end up, what's the new position? It's your starting position plus the area under the graph. So that's velocity, or that's the integral of velocity again. But this time we want the negative to remain negative and the positive to be positive, so we don't use absolute values. Okay? Now, symbolically, that's going to be the starting position. If we use, say, x of t to be position, the starting position would be x of 0. And then this would go from 0 to whatever new time frame we were talking about. Okay? Distance is always positive, but when you're looking for a new position, you care about whether you're going left or right. All right, study those. Today's work is going to be mostly visual, okay? Most of the problems are going to be just like that turtle where I give you the picture and the graph and you just interpret it mostly common sense. Okay, there are going to be 2 problems though where I give you an equation like this. And I have to tell you what P of T stands for, which I didn't do here. I have to tell you in person right now. If this stands for position, okay, I'm telling you that this is position. Now answer these questions. Well, hopefully remember that velocity was the reasoning for all of our things. So the first thing we would want to do, if I give you position, the first thing you should do is first find velocity. Okay, I messed that up. Here we are. Okay, back to the calculator question. So first I'm going to find velocity. Technical difficulties. So the velocity would be the derivative of position. So I do the derivative. Oop, that's a typo. Also, I meant for this to have a 3 right there. So again, if this is position, all of my reasoning all has to do with velocity. So first we're going to find the velocity equation by doing the derivative. So power rule, we get t squared minus 5t plus 6. And then if it's a calculator question, you can literally graph this and answer the questions the same exact way we did with the turtle problem. Just look at the graph, okay? All right, and I'm not going to answer all these. I just want to give you that hint. But if it's a non-calculator question, same exact problem, but non-calculator question, now you have to answer all those questions. And this is all review, by the way. Now you're going to answer those questions by hand, which means still find velocity. Still use your justifications. Well, I'll do part B for you, for example. Moving to the right would be when velocity is positive. Well, this is velocity now. To find when it's positive, I do a sign chart. Set it equal to 0, factor. Set each factor equal to 0. Now put that on a velocity sign chart. Okay? And test the sign of your velocity using the factored form. To the left of 2, we would get positive. In between 2 and 3 would be negative and then positive. So to answer that question, when is it moving to the right? We would say here and here when velocity is positive. But remember, time can't be negative, so we would chop this off from 0 to 2. So we'd say the answer to part B would be from 0 and including 0 to 2, and then also from 3 to infinity. We usually use open parentheses because at these points, that's not a positive velocity. That's where the velocity was actually 0. But in this case right here, that graph was really going right through the 0, so we include that one. Okay, so if you can't use a calculator, you have to do a sign chart. Part C, think about that one. How would you do that? Well, acceleration is the derivative of velocity, so we would have to do another derivative. Okay, find acceleration would be 2t minus 5, and find when that's positive by doing a sign chart of acceleration. That's all review. There's nothing new there. So set it equal to 0, we get 5/2. Make an acceleration sign chart. Plug in numbers left and right. If I plug in 0, I get negative, then positive. So when is the acceleration positive? From t of 5/2 or 2.5 to infinity. Okay, most of that is review. I just wanted to remind you, if it's a non-calculator question, you're going to be doing sign charts. But if it's a calculator question, just put the velocity equation into your calculator and interpret it on the graph. All right, good luck. Hopefully it's easier than I make it sound. Bye. Let me know if you have any questions.